So my slide is visible, sir. Yes, now
Yes, yes.
Yes,
now
Perfect.
moving.
absolutely.
Yeah, it's moving perfect.
Okay, perfect. Thank you, thank you.
So I guess you slept well.
Yeah,
You
yeah.
rest.
Because what happened is that some yesterday I had some Indonesia, some people have invited me, some known people, some
Uh-huh.
conference, So it was not really good sleep. Still okay.
Okay.
Yeah, yeah, yeah. So you told that you previously you are there in some in France also somewhere. Some which city sir you are there? Which laboratory?
Yeah, I did postdoc at Leuven.
Okay, okay, okay,
I
okay,
was there for almost 2 years.
okay, okay.
Then I,
So you know that you might have known the magnetic like a Revo, like our ICMCB, where in Bordeaux, a lot of magnetic material group. Some people are working. Maybe Revo is you people are you familiar in
uh,
the yeah.
then I was there in France also one two occasions, but not
Okay,
for a
okay,
long time. Long time I was there only in Leuven
okay, 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 sir, okay, sir,
because I joined job here during my
okay,
PhD.
okay,
So
okay, okay, okay,
so I go for postdoc with leave.
okay, 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 okay. So very nice. First time I'm able to visually present your future. We will see. Although in this
Yeah,
a lot of places.
maybe in near future because I organize one international conference. This
Okay,
is
sir.
material science in every 3 years. So
Okay,
last
good, sir.
time I organized in 2020 March. So a lot of people participated from different parts of India also and outside
Okay.
India also. So maybe if everything normal, then we
Yeah,
will
yeah.
meet somewhere. But anyway, we'll be in touch.
Yeah,
So
yeah.
you are working there?
Yeah, yeah, yeah. Me, yeah, okay. So presently, just like you might know the previously I was there in the physics department, NUS, National University of Singapore. So almost 16 years, 17 years I was. It was very easier for me
Yeah.
since now it is almost due to COVID. Everything life is almost for the last 3 years. I'm like we stuck in one place.
So you visit India often or very less?
I used to come. I used to come. Now it is everything is due to
Yeah.
Corona.
Now is everything stuck. So next
Yeah.
time when you visit India, you
Okay.
inform me. Then we will plan some program.
Okay, sir. No problem. No problem. Anyway, then we can plan because this different area, So
Yeah.
yeah, definitely, definitely, definitely.
So you are from which part of the India?
So I'm from Bangalore, South,
Okay.
Bangalore, Karnataka. Like people will call it Telugu. Since my name is surname is Reddy, so people think that I'm
Yeah.
Telugu also.
Yeah.
Officially, actually, I'm both Kannadiga and officially Kannadiga. So surname because I'm borderline cases. Yeah.
Okay.
Good afternoon, everyone. I welcome you all on behalf of the Department of Physics, Tripura University, into the last session of day 3. Dr. M.V. Reddy will gonna give his lecture in this session. Dr. M.V. Reddy obtained his PhD in 2003 in the area of materials science and engineering with highest distinction from the University of Bordeaux, ICM-CB, and CNRS, France. From July 2003 to May 2019, he worked at the Department of Material Science and Engineering, Chemistry and Physics, National University of Singapore. June 2019 to August 2021, he worked at the Center of Excellence in Transportation Electrification and Energy Storage, Hydro-Québec, Canada. Currently working as a senior professional researcher at New Graphite World, Montreal, Canada. Over the past 20 years, he has conducted leading research on materials for energy storage, solar cells, electrocatalysis, and photocatalysis, and the evaluation of functional properties of materials, development of in situ techniques, and materials for renewable technologies. Dr. Reddy has published around 200 papers in various internationally reputed journals. He has obtained an H index of with 66 over 16,100 citations. These have recently placed him within the top 2% highly cited researchers in energy. Dr. Reddy is serving as an editorial advisory board member in Materials Research Bulletin and Journal of Energy Storage, as well as several open access journals. Dr. Reddy has conducted several workshops and delivered 20 plenary, 25 keynote, 90 invited, and 18 contributory talks at various conferences. He has got some prestigious awards like Outstanding Science Mentorship Award from Ministry of Education Singapore and an Inspiring Researcher Mentor Award from NUSHS, 2021 Battery Materials Electrochemistry Award from the Electrochemical Society of India, Indian Institute of Science, Bangalore, India. Invited life member in the International Center for Diffraction ATA, USA. He is an elected committee member in Institute of Physics, Singapore. Material Research Society, Singapore. He served as an honorary auditor, IPSS and MRS, Singapore. Global Materials Network. He served as a theme chair and session chair for various international conferences. He trained many high school or college and international exchange BTech, MS, PhD students and personally mentored 7 students for electrochemistry and material science and engineering. I welcome you, sir. Please take over the session.
Okay, thank you. Thanks for your kind words. Better, I'm going to share the. I think I have to share the entire screen if I remember. Share. So whatever the slide is visible.
Yes, sir. It is totally visible. Fine.
It is moving.
Yeah, you go on. It's moving.
Okay, perfectly fine. Okay. So once again, thank you very much for your. I think for you, it's good afternoon. Me almost 5 o'clock, exactly five something. Okay. So again, good morning, good afternoon, everybody. So best I'll put my timer on. Make sure that I will not exceed the time. Okay. Okay. So again, thank you, Professor Saeed, uh, for his organizing the excellent workshop on the 2D materials. Again, I think for me, the first time to present this type of in Tripura University, also in the almost like this region in this, okay. And also thanks to for the technology, so that at least we're able to virtually present and discuss our especially what are the research activities we have. So today I'm going to discuss some novel materials for energy storage applications, maybe in terms of synthesis and characterization application. Again, since this conference, people have been, the important theme of the conference is the 2D materials. So now, so again, if you see this, for example, energy storage, so 2D materials already known. For example, you take a graphene or something like graphitic or molybdenum sulfide, titanium sulfide. For example, titanium sulfide is also almost like 2D material, or tungsten, molybdenum sulfide. They're all the 2D materials are used for energy storage. Anyway, due to the, for example, TiO, TiS2 or molybdenum, although we can use this electrochemically, we can use this, we can study a lot of physics as well as a interesting what they call electronic properties, especially for batteries. We have some limitation, the what they call energy density. That's why we cannot use practically something. Oxides are better in terms of the voltage. So anyway, so I'm going to in my presentation I'm going to discuss about some sulfides, mainly oxides, so that especially layered compounds during the presentation, how we can prepare the material, etc. So presently I based in Quebec, where the French and English speaking state. So again, we can see we can get some different type of seasons, especially January, February. Sometimes you may see the extreme climate variation, and also especially now in the, for example, June, July, and September. Now I think all the leaves are going to, color is going to slowly changing. I think sometime depending on the yellow, some cases you can see there is all, and then soon you may go to somewhere like this type of trees or somewhere here. So these are my outline of a presentation. So I'm going to introduce the things. So especially in Singapore, already a lot of students have been trained in the area of what they call as nanotechnology and then material science and engineering. These are this few young students starting from junior college, and some few students are high school. So it is almost like a 1 year or 9 months program. So students can come as a part time whenever during weekends or during weekdays whenever they have the experiment. So usually, as you can see, many students are able to present in the various conferences, for example, various programs. So as a consequence, some students are, especially few students, were able to publish the papers in the various international journals. So it clearly shows that we have some facilities, and with some ideas, I think anybody we can do the research. So that is not a major issue. So some students are able to present in the presentation in the where the conference is held in Singapore, as well as other part of the world, for example, USA, Intel International Science and Engineering Fair, and Poland, and also in Japan. So these are the small group from NUS. So we almost like 4 to 5 PhD students have been trained, and also in addition we have a lot in India from lot many students have been nearly 6 to 7 PhD students have been trained in our laboratory. So and also a few other people from Iran, and also some UCL and other places. So these are my small collaboration within Singapore as well as in India with various universities, as well as other part of the world. So again, so today I think some maybe since the novel material workshop, so I'm going to discuss some few examples of novel materials we've contributed here, and also some of my other interests are supercapacitors and especially electrolyte and some other areas. Due to time limitation, I'm not able to discuss all the things. So now all people are familiar that the materials and human history and prosperity divided started in the Stone Age, early Copper Age, Iron Age, and Rubber Age. Especially Silicon Age made them to think in a different way because they discovered vacuum tubes and, for example, computer, and then especially the iPhone, etc. So again, early, I think around 1980, I think composite age, again, they call lightweight materials, for example, aircraft, or a lot of the interesting things happened in the area of the composite technology. That's why nowadays you can see very lightweight material, lightweight, all vehicles are lightweight, etc. And now, I think year 2000, what they call as a nanotechnology, at the time, there is a lot of interesting things has happened. So everywhere, I think huge area, especially in this area. And year 2020, what they call as the molecular ages, and the future always we call as the intelligent materials. and low carbonage. So that always people are talking about the how to protect the environment and how to protect the pollutions. Any irrespective, any whatever the way you material do, for example, CO2 capture, or for example, how do we can reduce the CO2 like that way. So again, for example, one of the hot areas already recent years, I already mentioned that energy, water, and healthcare, and maintaining sustainable environment and healthy lifestyle, waste management, and reduce the air pollution is required for any smart city development. I think that's why everywhere. So that's why. So it is very important. Our job is to look for at least something, some contribute. That's why academic institutions like us, at least we can contribute to for the society in terms of there is respective areas. Not like all the things we can do, one person cannot do. Again, the materials we broadly classified based on the utilities, and for example, building material and phase change material, for example, electronic material and energetic material, and then for example, lightweight material, etc. Especially based on physical properties, I think this conference has been already many interesting talks has been covered with, especially in terms of metals and this type of areas, especially magnetic materials. Again, optical material, I think some specialized talks has been covered with, especially especially if you talk about your chalcogenide 2D material, I think they have interesting optical and photonic and already different type of physical properties have been reported. So again, dielectric. Today, I think in my presentation, I'm going to discuss materials related to the energy storage, electric vehicles, etc. So to again, I think always people are talking about the environmental, how we can do the green renewable technology. Again, it will vary depending on what type of available sources. For example, from here, we have a lot of hydroelectricity, especially places like India. I think somewhere we have a lot of heavy solar energy, not only India, some other Middle East, etc. And batteries are also one of the important things throughout the world. So that's why we want to reduce the pollution. So I think these are the electric EV market is booming in all over the world. So anyway, other thing, bioenergy, fuel cells, hydrogen storage. Again, I'm telling each technology has another advantage, limitations are there. So and I don't have much time to discuss. So today let's try to focus on the especially novel material related to the batteries. Another one is energy storage and renewable technology. Always you can call as is a multidisciplinary. That's why we need the expertise of science. I think sometimes we know that some people are already there, some physicists also there, chemists also there. I think we need the expertise of this one. Means since you want to prepare the material, we need good chemists. Or suppose, for example, you want to understand the good physical properties or do proper measurements or some institute development. I think we need the importance of physics. Again, engineering in terms of since it's a big device, a big pack, we have to work with the material production and for example, large scale, we need a chemical engineer, mechanical, etc. Again, automobile and electronic, and again at the end we need some management. So again, suppose for example, in this particular area, say especially research is needed to look for the novel materials. Again, try to understand how the synthesis are processing and characterization for the future energy storage applications. So these are the one slide. It will show the importance of the batteries. For example, you want to store the uh, solar or wind energy. So we can use this type of material for just to store the things. And then advantage of this, for example, like renewable energies. I think we can reduce the CO2. So again, this is the world data. So still the petrol price, crude oil price keep on rising. So, so again, remember, so depending on the what energy you have, for example, smart grid and electric vehicles, there we need a little bit more energy. It clearly indicates that, so we need more materials, more material or more. So that's why here the main cost safety comes into the picture. That's why you have to look for something like a high performance, high energy density material to solve the especially smart grid and EV application. Anyway, portable already, for example, your iPhones, laptops, everything has been whatever the energy requirement is low, and then already the technology has been solved in. So these are the small, for example, people think that if we reduce the gasoline vehicles by EV, by battery operated vehicles, still we can reduce the further pollution, especially in the major cities. So another important area, for example, if you want to store the solar energy, again, although suppose you want to store the, for example, sometimes nights, we need a affordable battery pack, in the sense that if your battery pack, the cost is keep on rising, at the end people may not be, so again the cost of the solar energy technology also is going to be higher. So that's why it is very important to look for the affordable battery pack. So another important area is that autonomous vehicles. Already, if you people are familiar, because somewhere, so these are all some already some few things already been tested. So it uses driverless. It uses technology. Autonomous vehicle uses self-driving vehicles, uses artificial intelligence, and it uses lidar and radar sensing technology. The major benefits of the autonomous vehicles is lowering the fuel consumption and development of smart cities, and reduce the CO2 emission, etc. That's why, so and also we can reduce the vehicular crashes. So it clearly shows that, so for example, this type of autonomous vehicles, again, we have sensor and then central processor, and for example, somewhere battery, somewhere here, and etc. So what I'm mentioning, that this particular device, I think we need the expertise of the scientist, both scientist and example. Although we can climb some, we try to prepare some materials. Again, you want to put it in the big pack. Again, we need the material and chemical engineering efforts. And the end, you want to integrate, we need some mechanical engineering, mechanical engineering or electrical engineering, or you want to write a program, everything you want to control with the computer, we need the computer engineer. That's why it is like multidisciplinary area of research. So these are the different companies are investing. So for example, Tesla, already people are familiar. So some other companies also. So it is known. So now I'm going to introduce, I think all people are using their this type of mobile phones. So somewhere you may see this type of the particular cells. For example, some they call it post cell. So all people are using laptops. It uses something like 18650 cells, or put it in the, for example, depending on requirement, maybe something like 8 to 9 or 12, depending on the stack they can put it. And future, if you're running with electric vehicles, what they use this type of this cylindrical cells, put it in a different type of stacks. For example, almost like, for example, this type of EV vehicle or battery pack, it is almost like nearly 7,000 cells. Seven. That's why if you go for large scale, again, especially EV, so we need the importance of the what sensing, example, safety, what they call battery management and thermal management, etc. So in summary, so materials are same. So the only thing is that, for example, depending on casing, depending on the requirement, I think we have a lot of big industry. They're able to, so all automated facilities are available, and they can fabrication, especially those are things are available. Although as academic researcher, you cannot do this type of big cells, and it may not be, sometimes people, no PhD students are interested to do preparing kilos of content. At least you can do as a industry, any R&D also, they do something like coin cell, the small cell, button cells you can do, and try to understand how to calculate energy density, understand the physics and electrochemistry or materials point of view. At least that will be very good for us. So once you get high performance material, I think anybody can do the research, especially novel materials if you do. So you really don't need to do very large scale. At least you coin cell is enough for us to at least which material is working well, and that way it is good for the community. And then try to, if you have high capacity, just to report it, and we have to mention that what type of voltage, and understand the mechanism, that will be good for us. So these are one small slide to show that, suppose for example, in a Tesla model vehicle, it contains almost like 18650 cells. Almost you see that the NCM means lithium, nickel, cobalt, and aluminum doped cathode. So it is, you can see almost like 7,100 cells of this particular cell that put it in the pack. So again, remember, so here there is a lithium containing compounds are there, stainless steel current collectors are there, and so that's why cost, it will vary depending which are all the raw materials, which country they have, for them it's easier. So what are the smart materials for electric vehicles, or for example batteries? Always you have to look for high energy density and power density. I'm going to mention next coming slide how to calculate the high energy density for example, energy density of the either any chalcogenide or 2D materials or any type of the oxides or etc. What are the important points into consideration? I'm going to discuss in the next coming slides. So again, at the end, we need high capacity, lightweight, and it's very important. What are the batteries to adapt the climate condition? For example, we know that we are using this electrolyte in these batteries. Sometimes if it is too low due to conductivity variation, sometimes it may not. That's why it is the optimum temperature. It's also like room temperature. So usually the extreme temperature means high and low, everything has to work. And long cycle life, more reliability in the sense that, for example, so long, for example, once you use this one, it is like a diesel engine, lifelong. Still, the challenges are there, especially long in terms of size. Another one is the working voltage, and then we always should look for the anode and cathode. There is a, for example, you do any chalcogenides or any type of oxides are not way to. It is very important. That's why. So there is a limit. We cannot use many chalcogenides here. Because there is a problem of the working voltage. Also, we can do some fundamentals in practical things. We cannot use this type of some chalcogenides in the real battery applications. And Coulombic efficiency is the difference between the charge and discharge. So that's why always 99% it comes is good. So low impedance means the resistance of the cell in the sense that once you fabricate the cell, so you have to get a minimal variation. Or suppose in case you fabricated cells is getting some 100 ohms or 10 ohms, whatever the ohms in that resistance should be. After long-term cycling should be, suppose if it is 1000 or 2000 cycles, 100 ohms becomes 1000 or 2000 ohms is something going on with respect to battery. The problem with the electrolyte or some problem with the what they call a side reaction, parasitic reaction. That's why this technique is very useful. Without opening the battery, you can tell that safety or state of the batteries. You can tell that what are the, it is like diagnostic tool, I can tell. Again, fast charging, I think these are the very important point raised by some many people. So why don't you use this fast charging? It means that people are looking for the, you hook the battery like your plug electrical like a car into the particular charging system. So they want to charge within few minutes or one minute like that. It's a little bit difficult because these are the solid state materials. So there is a problem with the diffusion. It means sometimes too fast charge they do. So then all materials may not be fast, and something problem with the kinetics. So as a consequence, so the like diffusion limit as a consequence, what use the programming they do is it in a low current rate, and they'll put the some safety limit. I'm going to explain how the charger is going to work for a any like commercially or lab scale setup. After doing all this one, we need low, safer material, low cost and toxicity and sustainability. So it is very important if you take your 2D materials in sulfides or anything, always these are very important points you have to consider. That's why sometimes if academic research, sometimes we solve some of the all the points, sometimes we may not solve this working voltage. After solving all this, we have to solve all other points. So that's why it is like industry concept is working is way is different. Again, at the end, we have to look for sustainability and recycling. What are the way, either sulfides or oxides, or at the end, we have to recover the material and then reuse it for secondary other applications. So now I think sometimes people may arise that cost of the batteries. Again, cost of the batteries depending on which type of, for example, so we need a raw material, for example, lithium, we need a, suppose, for example, lithium mining, we need, and this type of elements we need because this one we can use it for electrolyte, etc. Or, and cathodes we can use. Another is the anode side is the graphite because we know the graphite can be obtained by using some graphite mining, something like a naturally occurring mineral. And also you can do some petroleum pitch. That's why here the mostly, so sometimes I think the problem with the petroleum pitch is artificial graphite is high temperature, so that's why we need high temp. So for example, if you have natural sources, I think there the production the cost will be lower. For example, here in Quebec there is a extensive like a lot of graphite mines, and that's why they're extracting, and they can use and then use it for the electric vehicles for the anode material. Another important point is the copper, aluminum, stainless steel. These are manufacturing. Other, for example, battery pack. We need something like permanent magnets, neodymium, dysprosium magnets are needed, especially to run the electric motor. That's why these are all type of the raw materials, which are things they have monopolized the things. That's why sometimes we depend on some raw materials. We depend on the particular countries. So that is the way it will work with the industry. So usually the mining and electric processing, electrochemical testing and manufacturing large scale, and end use and recycling. So these are the typical things in a battery. If you see the cathode side, depending on which type of the things, depending, I guess the cost is going to slightly vary, and the anode and separator, etc. So that's why, so the cost of the batteries will vary depending on the mainly, I think we have to reduce further. So for example, too much of cobalt is there. That's why nowadays people are reducing cobalt by nickel rich compound, etc. So now I'm going to introduce the fundamental a little bit more on the how the your components of the batteries. Again, I'm mentioning that so you can see that the first work in Whittingham, all people are familiar. So these are all the Michel Armand work on the iron cyanide bronzes, followed by I think second paper or second things is really I think TIS2 is color. There is also one is 2D material. Now we people call it chalcogenides have been already tested. Only problem is at the time is fundamentally the only thing, the voltage is slightly lower, so we cannot expect high energy density as we compare to the standard lithium cobalt oxide materials. So now I'm going to introduce a little more depth, so that like the cathode, so it contains something like if you call it the lithium batteries, the lithium containing cobalt oxide or lithium iron phosphate and lithium manganese phosphate, etc. So this type of the materials put in the binder and then connecting carbon, they can finally coat it in the aluminum foil. So this cell is, this side is the, okay. Suppose if we wanted to do with sodium battery, we need sodium containing cobalt oxide or any type of sodium compounds you put there. So exactly like potassium. I think you people are familiar about it with ionic radius, means lithium is slightly more lower ionic radius when compared to sodium and potassium. As a consequence, there is a mobility issues, and also you see that stability of these elements. For example, you see that so sometimes is more iron. Again, you see the reactivity sodium and potassium is slightly more when compared to lithium. So especially for the water. So that's why, and also these materials are a little bit hygroscopic. For example, we have to see this material, keep it for exposed in air. Sometimes it will absorb the moisture, sodium containing compound. That's why we need a dry room, etc. So in case of anode negative electrodes, usually we use a graphite. It's a very per layer type compound for in case of anode, or sometimes lithium or potassium or sodium, depending on what type of cells you are going to use, or in combination of graphite or carbon or some silicon, tin carbon composite, something like a metal oxide, etc. Or sometimes people want to be the calcium battery. We can need respective ions. Again, remember, so calcium is a little bit more, for example, flammable, it is more reactive to the water, etc. So it is very important. So what are the way, either cathode or anode material, for example. So once you make a cell, so I think we need to avoid the short circuit. That's why to do that one, we need a polymer separator. And the science has to move here and there. They do not like that. So we need something electrolyte medium. So sometimes we use something like Livpo4 CDMC. Sometimes ionic liquid and polymer electrolyte they use. So that once you apply charge and then movement of the ions. That's why here the main issue is that you take care of the electrolyte should be flame, avoid the flammabilities, and then sometimes temperature is to be same. Otherwise, if too low, the conductivity is going to be decreasing. So all things are the real challenges. So again, the binder dimension. So it is very important electrochemically. So this type of cells, for example, you want to study the physical properties or magnetic properties. For example, cobalt oxide is a superconducting material. For example, you can remove the lithium and we can understand the more fundamentals, etc. That's why it is like either physicist, lot of things you can do depending on really what you want to do accordingly. So and also something like interesting, what they call electronic properties also we can study in addition to the battery performance, etc. So these are the 2019 Nobel Prize is given one of the well-known physicists. I think all people are familiar with Professor John Goodenough. He's one of the oldest, 19 years old, oldest Nobel laureate, won the Nobel Prize. And in addition to all three persons, I think Michel Armand also play an important role in the development of the rocking chair and polymer electrolyte, etc. You can see this, for example, I think all people are familiar that these are the word, something like Jean Roxel is also one of the all layered compound is one of the early work with Roxel from the NIMN nons. I think one of the well-known solid state chemistry has been contributed with the early all our bronzes and then 2D material, etc. For example, sulfides, chalcogenides. I think I'm talking about almost 1970, 73. I think these are all the people who have been trained with late Professor Eigenmuller is one of the father of the solid state chemistry or the material researcher in Singapore, what I'm telling you, in France, and well known. So in fact, he visited all over the world, including India and then Singapore, etc. So, so what I'm telling, that all their original discovery made them to think differently. That's why. So at the time is I'm talking about almost like 1970. At the time, they used to study the physical properties. For example, sodium cobalt oxide. At least try to understand the magnetism, etc. At the time, then finally some collaboration or something exchange. Professor Jan Goodenough visited the ICMCBR Bordeaux. So at the time, people have different ideas and. So since both solid state chemist, why don't you replace by lithium by sodium, sodium by lithium? Then again, so he discovered the lithium cobalt. I mean, he tried to prepare the sample and use the test material for the battery. Just you can see that how the voltage can be, we can see, and finally, sometimes based on the issue, with the graphite, and they made a full cell, and based on that one, now they Sony introduced this, especially the lithium ion battery technology. So now I'm going to a little bit more detail. I mentioned the components of the cathode anode and what are the materials you can use. So now, so I'm going to mention that what are the important uh, important characteristics. For example, so these are cathode materials. It contains a positive electrode, a negative electrode is anode. So what will happen during charge? Lithium move from the cathode to anode, where the electron will pass to the external circuit. During discharge, a reverse reaction is occurring. So that's why we call it the rechargeable batteries. So typically, if you suppose, for example, lithium cobalt oxide, when they remove lithium from the structure, cobalt 3 plus to 4 plus. So what will we get a positive current and negative current. So that's why we call as a rechargeable. Same material, for example, lithium cobalt oxide, the Galvanic voltage versus capacity, where we may get something like 3.9 or 4 volts, etc. So now you remember, so this voltage almost reasonably, so suppose for example, depending on which type of cathode they're using, these are all layer type. Remember the lithium cobalt oxide well known is layer type compounds. So when we need something, we want to be good voltage, we have to get a difference between charge minus discharge. Now, people may ask you, why don't you use your layered compound, for example, tungsten oxide or a molybdenum sulfide? Yes, we can use. The problem here is that, molybdenum sulfide is, for example, MOS, the molybdenum is in, depending on the oxidation state, MOS2 or S3. So there, we cannot charge, it's not possible. Like already is higher, we cannot, only what usually we can do is that we can discharge. The only thing is that there is a possibility we can intercalate the lithium. For example, MOS2 react with your layered compound, react with lithium metal, then you get LiMOS2, means like one lithium we can do. So as a consequence, you may get something like voltage, this type of higher voltage we cannot get. Okay. So that is the reason, for example, the early work on iron sulfide, titanium sulfide, everything, only you may get something like around 1.5 or 2 volts cathode. Okay. So then it may not be. So for example, these are the nearly 4 volts, so volts peak. That's as a consequence. We are not, and also we know that sulfides, because depending on the metal oxygen bond, uh, for example, metal sulfide bonds are not really good when compared to your metal oxygen bond, and metal to phosphorus bonds are seems to be good. So that's why, and also sometimes these are sulfides, they react with electrolyte and sometimes moisture, etc. That's why, so they're not much materials can be used for the energy storage. So now, so we materials, including your chalcogenides or oxides, etc., broadly classified into the 4 categories. Suppose, for example, your TaH2 layer type chalcogenides, within one lithium, you can do, there is also called as the intercalation type of things. Or if in case of tungsten oxide or molybdenum sulfide, if you cycle to lower voltage, for example, this up to 3 volts, we call it a conversion reaction. It means that, for example, your molybdenum sulfide is a 2D material, react with the lithium, we'll get right to molybdenum metal. So and Li2S. So that is also as this type of conversion reaction is occurring. The problem here is that as compared to the oxides, again we have some problem with the voltage hysteresis. Means if we cannot use these materials if we want to make a full cell out of battery. So we don't have any proper matching cathode. So because of the higher discharge and charge voltage for this type of the compound, including your oxides, chalcogenides, or nitrides, etc. So now, as of now, the most commonly promising mechanism is the intercalation, including a graphite or commercial cathodes, etc. It will undergo sorry TiO2, etc. with one lithium because we don't see much volume variation. That's why this mechanism is more popular. Okay. So again, if you take alloy forming element, for example, silicon, tin, and we can farming something like you can see some volume expansion during the discharge charge. That's why people they use something like nanotechnology mixed with some carbon matrix, etc. And they can do to avoid the buffer the volume variation. You can do. Another is the alloy-based conversion reactions. So again, if you talk these materials just to depending on the voltage, although you may get slight higher capacity, there is some limitation in terms of voltage, hysteresis, etc. Anyway, practically any anodes or anything, always it is nice if you cycle, if whatever the capacity you'll get with the below 1 volt, if you get, that is good for the practical applications. So now I think we get some idea about these mechanisms. Now, slowly, I'm going to tell that, suppose, for example, any new researcher, what type of the materials you have to look, either cathode anodes, and then always the term point is that you have to look for the material should be low atomic weight. So, as a consequence, any new materials, either chalcogenides or oxides or phosphate, whatever it may be, so you have to look for low formula weight, so that automatically we can the theoretical capacity. This denominator is lower molecular weight, automatically it will go higher value. So it means that Faraday's constant, the number of lithium, etc. we can get. Another important is anode. You have to, for example, voltage versus capacity. Whatever the plot of something like discharge potentials, you have to get lower as possible is good. I think around 0.2 or for example 0.3 or something if you get is good. Sometimes, so if it is cathode should be higher. For example, depending on the like a lithium iron phosphate, or lithium cobalt oxide, or some other high voltage materials we can get. So usually best way is that higher is good for the practical application. Now voltage itself is nothing but average potential of the cathode minus anode, means something like charge potential minus discharge. So that way it will get some information. So again, so as a consequence, we can calculate energy density. That's why voltage cells multiplied by capacity. There is a reason. This is very important. Determines your EV market. For example, you want to reduce the cost, or you want to something like, for example, reduce the weight, etc. So now we need something like extended plateau, means that 200. We can, if we have any good ideas or new materials, go for 400 milliamps. I think that will be very useful for the practical applications. So again, in principle, material must not soluble with the solvent and electrolyte. So this is very good thing. And ideal cathode anode must not possess. It is very important. Sometimes people are talking about your fast charging. We need something like mixer and conductor is very important. That's why. So for this case, people want to use further improvement conductivity. They use something like carbon coating, etc. Or you can use something like graphene, like layer. Also, you can do, or some other type of nanotechnology, or sometimes small 2D coating materials also you can use. So in summary, so compared to your other type of lead acid, there other type of technology, again, these are lightweight and then because of the this important importance of the higher voltage, people can use it on large portable applications and space as well as drones, etc. These batteries are going to use. So now I discussed earlier previously I mentioned the fundamentals and cathodes and anode what are things. Now we have to understand what are the electrolyte. Electrolyte is something like a medium to pass to cathode to anode ions. That's why we use something like inorganic salts. If it is a lithium-based system, we need a respective salt. For example, you take potassium, sodium battery, you need sodium containing salts or potassium, etc. So that's the reason. So it's very important. Good electrolyte should has to get good conductivity. It means reasonably liquid electrolytes are really good, and and also we need to get something like also some are disadvantage. Not really. So sometimes I can tell some cases we may see some flammability and leakage and sealing issues for this to avoid this one. So I think people have been looked for other alternatives, something like polymer electrolyte. Again, polymer electrolyte dispersed in the ionic liquids, etc. Again, we need slightly higher temperature to get a reasonably good conductivity. Separators are the very important materials. Avoid the short circuit, already mentioned that, and we have to look for the optimum thickness, porosity, and permeability, and good electrical resistance, and good tensile, etc. So again, nice suitability puncture, because it's very important. Sometimes depending on eye rate or current, sometimes temperature, if the separators will shrink or some problem with the dendrite, there's a small puncture is happened, then it once it's shorted, again the battery is going to fail. That's why if you're almost like around 7,000 cell, one battery is going to failure, then it may get all lot of other things are going to disturb. So now I think safety is a big issue. Sometimes people are talking either flammability of electrolyte or oxygen release from the structure. This point I'm going to discuss in the last time, how the material, for example, sometimes you may see increase the safety limit. For example, particular things, sometimes you remove too much lithium from the structure, you may see some volume variation as a consequence, or some materials are highly reactive to the electrolyte, etc. So now I'm going to the reason for this, why recently, so the another is a solid electrolyte, so that were mixed with some ceramic membranes with both either oxides or sulfide based electrolyte, and mixed with cathode and press into something like by hot press or something like hot press sintering, and we have to go to slightly higher temperature. The problem here is that that if you want to prepare like a A4 sheet roll to roll, this ceramic membranes are a little bit large scale is difficult. Still there is, and also sometimes people want to be high current rate, etc. We can difficulties are there. Again, there is a lot of academic interest is going on, especially here, and also industry. They are spending either sometimes in combination something like polymer electrolyte in combination with ceramic membranes, etc. The people have been done. So it is very important thermal expansion coefficient has to match with both cathode and electrolyte, and good chemical stability, no crystal structure transformation should occur during the electrode near the sintering temperature. Again, so these are the very important points here too, and also conductivity also reasonable, means 10 to the minus 3 Siemens per centimeter is good for the applications. You see this the different type of either sulfides also there, and different type of compounds, and oxides based garnet based electrolyte. Again, each electrolyte have advantage, disadvantage in terms of processing, etc. For example, sulfides have good conductivity. If you talk about these are the, if you want to expose small and moisture, the hair it becomes hygroscopic, become smelly, and sometimes material stability. Again, oxide seems to be good. Again, you want to make a good ceramic membrane, we need high temperature, etc. So again, this one, if you want to use the ceramic membranes, so these electrode protect the solid electrolyte for the serum to protect the membranes, etc. So remember, these are all the different applications of the electrolyte, for example, redox flow or all solid state battery, etc. So now I'm going to quickly, I'll go through some material processing and characterize what are the techniques you can use. So usually we play with the periodic table, either lithium in combination of the metal oxides, either oxygen and phosphorus, etc., or exactly sodium, etc. So usual way is that depending on applications, since for example we are a battery, we look for one energy storage, or some people are a catalytic, or some people are electrical and thermoelectric or thermal property or optical, etc. So accordingly, the available facility and what they're really looking, so accordingly they can select the appropriate compounds and try to understand the structure composition either by size and shapes. So it's very important sometimes. That's why nanotechnology will play an important. We have any fantastic techniques are available to prepare the layer by layer materials with different type of physical techniques. Again, usually you have to understand the structure, size and shapes. Again, what they call as the material synthesis and characterization techniques. And especially characterization is very important to go for any applications. So these are the importance of the what I call nano, or what are the materials for the in terms of different type of applications. For example, nanophotonics, spintronics, aerospace, or healthcare, and energy, environment, or other type of sensing, other type of the applications. So, again, nowadays we have the capabilities, although lab scale we can do in a small quantity, especially industrially, also similar type of the size and shapes, everything we can do with advanced particle material processing. People can prepare the materials in almost like a tons of the quantity. For example, a lithium layer type compound, people, we have capabilities to prepare nearly tons of the quantity they're supplying, and that's why we need a, especially almost like, for example, we know that all this raw material, for example, this one nearly almost like 2000 metric tons, like 2000 tons in that type of very large quantity also needed for, especially for the large scale requirement, not like a milligram research. Okay, so now, as you also remember, as an academic research, at least we can do for a chemical method. At least we have the depending on oxides, and we can use appropriate chemical method. Later, you want to make a thin films or all solid state batteries. You can, or thin film batteries. You can use something like physical methods, or sometimes you want to study the magnetic properties. There, you need a thin films, or layer by layer. You can use something like different fancy technique, for example, ALD, etc. We can use. So another one is, for example, ceramic or metallurgist, or for example, people want to prepare all solid state batteries or solid oxide fuel cells there. What are the material you prepare in chemical? What are the methods? Then finally make a good compact. And so for that case, in what they call a particle to particle contact only is possible. Either you can do something like hot press or spark plasma sintering, or recently, if you talk about some other ceramic material, they can use it for 3D printing, etc. So it is very important if you look for any novel material, although the thin film sometimes we don't, your facility can do. For example, here, chemical methods, if you want to establish, usually either sometimes oxide, solid state method, or whatever it may be, novel method you can design. So make sure that you have to, before doing, you have to understand this, just check the charge and ionic radius to balance. So once it will balance, then you can try to prepare. Otherwise, although it is not so easy, sometimes you do trial and error and really what are the requirement, and then check the literature. So at least we are the people have done our best way that ICTD database. We can see, you can get the different type of compounds are. So please follow, read the old literature, etc. I think people have been done on the particular compounds. So now, once you prepare the material, is very important. You have to characterize them. So again, the importance of physics. You can use the X-ray diffractometer. That is very useful to understand the lattice parameter, outer impurity, and cation mixing is very important. And sometimes you can neutron and the X-ray absorption. These are all things you can do fancy thing. We can do some collaboration. So that's why we cannot easily access, especially XRD. That is enough for you to do the other studies, for example, charging, discharging, or okay. Again, if you're thin films, you have to do RBS, Rutherford Basket is a very useful tool to understand the composition and thickness. For example, lithium metal is a, you have to use nuclear reaction. And for example, bulk materials, we need something like chemical analysis or XPS for that to understand the valence state, etc., or what type of oxidation state, etc. And these are the different software people will use. I can, for example, XRD, Topaz, iScore, and PDXL, for example, you want to be thin films, and XPS and Caraware, for example, and Z-plot, for especially for the impedance. And we need the morphology and other characteristics, for example, IR Raman, especially if you have magnetic studies. Also, again, there is a good specialty of this for materials. We can do magnetic properties also. Again, thermal parameters. Again, VT, surface area, etc., etc. We need. So these are the various characterization tools, XRD and Raman. Sometimes you want to understand how the, for example, all people are familiar, especially chalcogenides or especially carbon or filial graphene. So this technique is very useful. So for example, the XRD is one of the very useful tool. A lot of physicists, I think any materials you do, we can have to characterize them, try to put some powder or any type of material to put it in the X-ray. So X-rays are incident on a particular diffraction occurs. So by knowing the interplanar distance and then Bragg's angle, diffracted angle, we can calculate the for example, lattice parameter like 2D sin theta is equal to n lambda. Based on that one, we can get the information about lattice parameters, etc. Typically, another important point information we can get, your materials are amorphous. We may see something like this way, polycrystalline or crystalline. So again, we can, and also sometimes your materials are nano size. We can see something like a line broadening, etc. So these are the different materials. Some other advantage of this XRD, we can do sometimes thin film. In a glancing angle mode, you can do layer by layer, what type of thin thin film thickness and different composition, they can check. So this is one example. If you see that also people can complement with their XRD data and then TM just to see the amorphous material, and then what they call nano size, and then crystalline material. Usually we take a diameter divided by 2, then 1 over D, then we'll get the D values. This D value what you are getting from this inner circle belongs to the D closed D value you are getting from the XRD. That's why we have to know the both the XRD and this TM, that will be good for you people. So in summary, in this presentation, I think we are going to touch up some few example. I think almost all the material researcher, we are in this type of 7 crystal system. So again, surface area is also very important point to remember. For example, people are talking about fast charge, discharge. Again, I think we need something like optimum surface area depending on materials. That's why, so it is not really, the values are not like standard depending on what type of materials are got. Accordingly, we need appropriate surface area, and also we have to get this type of isotherm. So again, for example, the shape factor by 6 divided diameter of the particle in density we can calculate, and also, for example, porosity again with in terms of the nano to macro porous, and also we probably classified based on the micro and mesoporous and macroporous depending on these are the IUPAC nomenclature. So most commonly, I think the type 4 isotherm seems to be good for our applications. So now we comes to the another thing, how to test with the electrolytical thing. Again, you can use the battery tester or impedance analyzer. That is very useful tool. Just you want to understand how the conductivity of the solids, or like more on physicist, you can same setup, you can use it for you want to see the you vary the conductivity, heating and cooling, and you can do a lot of interesting physical properties. So fast what a charger is nothing but what it will do is that this type of big, for example, your own battery charger for your car or whatever it may be. So inside the circuit there is a software, there is a system, there is a breaker. It will tell that okay, depending on the battery, there is a lower limit and higher limit, and also they have something. Each thing current is fixed in the particular charger. The current is fixed. So what it will do is that we can usually academic things is more accurate, something like more accurate, and also you can plot everything. Usual way we can calculate how much time is taking from here to there, the step time multiplied by current into weight of the active material. As a consequence, we can calculate the capacity of the material. So advantage of this particular technique, you want to see the energy density. Already I mentioned depending on a different type of cathode and which are the potentials are needed. That way, it is very useful for us to calculate the energy density. So this, for example, this is a typical energy density means average potential. For example, I already discussed battery into capacitor rating, and specific energy, and both are same watt hour, and then sometimes people they different rating. For example, 18650 cell nominal voltage is 3.6 volt, and then rating is 3.0, then cell weight is 45 gram, then 240 watt hour per kilogram. I think so. That's why this value is good for your electric vehicles. And also another one is the power density, then voltage into current, like that way. So I think this points already discussed about to calculate the basic formula. Experimental capacity means step time into current or mass of the materials. Theoretical capacity is nothing but number of lithium into Faradays into. So this way we can calculate the theoretical, any type of the either chalcogenides or any type of the oxides or phosphide. So irreversible capacity is nothing but during the usually in the first cycle, you have to get a lesser, these aren't really good, sometimes slightly higher ACL. So among them, 1, 2, 3, 4, you can see there's a graphitic one, there's a fuel graphene, and there's a graphene type means slightly higher surface area, graphene type of compound. You can, if you keep on surface area is increasing, you can see that we can get high capacity. The problem is this plateaus are like charge when it discharge is not really good. So whatever the applications you have to get somewhere like down. So whatever the capacity somewhere you have to get, this limit is good for the practical applications. Capacity fading is nothing but how much loss from the second to n cycle, when 50 or whatever the cycle you want, and multiplied by 100, you can get Coulomb efficiency difference in the discharge and charge. So from the R100 minus X, we can calculate. So rate capability is the one. So sometimes we may ask you that fast rate means like 0.1 C means C by 10 means 10 hours. So that's why, and same battery, if you run with 1 C means somewhere 1 hour. If it is 5C, it is 12 minutes. See, you can see 12 minutes, you are able to get, I think, around 60. The same thing with 1C, the same battery, if it is 1C, is like 120. So usually that's why as a supplier, what they'll tell you that irrespective, they wanted to compromise. That's why they always in the program they will tell, okay, please go to the doing charging at a low current rate. So that's why. So always sometimes we not to get high capacity. That is the main purpose behind this. So they mainly due to the diffusion limitations. So how we can improve the rate capabilities of electric vehicles? Again, either you can do some nanoporous material or material design, improve the electronic conductivity and electrode design. A lot of interesting things happened, especially you see the industry. So they think differently, and then a lot of their own patents and trade secrets are there, especially people are talking about the rate capability, etc. And also current collector modification, etc. Again, another techniques, the cyclical tomograms is useful to understand the cathodic and, for example, anodic means like, for example, we can see the oxidation and reduction. So from this, we can tell that whatever voltage or etc. So my suggestion is that if the solid state batteries, try to use low current rate. Don't use slow scan rate. You try to use. Sometimes we use fast scan rate. If you use solution electrochemistry, you don't see any curves. That's why you don't see much information. Always, my suggestion, do it with a slow scan. So anyway, with this technique, we can understand, for example, what type of voltage, 4 volt, 3.5 volts, or depending on what type of things, we can get the information about this redox potentials. So and also another interesting things also, you can see effect of scan rate or effect of, for example, you see any surface area, etc. We can calculate the sometimes we can understand what is going to affect, or we can see the what they call as a Randall's equation. From there, we can calculate the diffusion coefficients, etc. So another is the important. I told that impedance analyzer also very useful tool to understand the, for example, uh, to understand the mechanisms, especially ion conduction, etc. So these are the different areas. Not only lithium batteries, for example, chemical sensor, photoelectrochemical cells, and solar cells and fuels, etc. In fact, this technique is very useful. I think all physicists are known. Not only or you want to study some what I call magnetic properties or conductivity, etc. This technique when you can be useful. So usually, suppose people want to see the conductivity, just try to code the palettes in the both sides. Some from there you can see nowadays new standard setup like 4 probe. Everything thin films are there. Everything the stations are available is very more accurate measurements also we can do. So from there you can calculate the conductivity of the materials. So based on the thickness and then the what is the resistance and the area, etc. So either you can do some batteries. Sometimes the two electrode, the most commonly used is two electrode systems, or you want to be more what they call as a more fundamental. Or sometimes you may go for three electrode system. It's a little bit difficult. Practically, mostly use two electrode system. Either you can do something like a reference electrode, etc. You can do this type of three electrode systems also can do. So advantage of impedance spectra, just that in case of solids, so just you want to see grind boundary, bulk and grind boundary resistance, we can separate, segregate, and we can see that how the energy of activation with respect to the two types of things we can understand. And finally, we can see this is very useful for the solid state ceramics. So that's why, so it is very nice to understand more fundamentals, etc. So it is typically when a batteries, we will get one semicircle somewhere here, and after charge discharge, we can get 2 to 3 semicircle depending on the voltage and cycle number, etc. From there, you can do something like a one resistor, one capacitor, depending on one semicircle. If it is two semicircle, we can use two resistor and two capacitor. Or if it is three semicircle, accordingly, we can build by using something like software, everything called Z-plot and sorry, what they call it, yeah, Z-plot software, ZView, etc. So we can do something like surface film resistance, charge transfer is the electrode electrolyte interfaces, and bulk resistance somewhere here, and Warburg resistance. So remember, it is very important, at least important of physicists. That's why you have to. We need. Luckily, we have all in-house facilities. We are more specialized than the impedance spectroscopy, and sometimes many people are interested in more depth to try to understand this particular technique. I'm happy to help, and please feel free to contact me if later if anybody is interested to understand how to interpret or how to do modeling with respect depending on circuits. I'm happy to uh, inform you or send me by email. I can happy to help you people. So again, although it is very analysis we can do, for example, we can do very nice analysis. You take the data. Again, interpretation is very complex. It depends on, and also, for example, this particular system we can do different type of system. Again, really, what is your what really you want to tell? Make sure that fix one particular system. At least you can try to understand what is the respective voltage or cycle number, just to see what is going to happen. So that will be very good for you. Okay. So is at the end, whatever you make a big the system level, I'm talking cell level. When you want to integrate big battery packs, they put it in the your electric vehicle. Again, you have to talk with your mechanical engineers, electrical engineer. That's why it is like interdisciplinary. You can see we need to understand the power electronics and electric machines understanding. Again, we need to know that how the permanent magnets are battery management. So something like, for example, energy and how the battery management also you have to understand, and energy storage system, etc. Suppose, for example, a battery means too many cells they put, there is a sensor, and just you have to monitor to make sure that all the cells are doing charge and discharge, everything is individually is going well, and sometimes temperature, sometimes those are all things you have to monitor. So these are typically, for example, you can see so many cells are again, this seems to be good here. We can see the voltage will be different, Similarly, during discharge, some cells are a little bit okay, and sometimes you may see the difference in the voltage. So that's why this battery management software is going to take into consideration. So now I'm going to talk about some few materials. For example, so again, cathodes and anode materials again. So the main issue is again the capacity somewhere here is limited. So these are lithium containing cathodes. So either if you want to be sodium, you need a sodium containing material. Again, anode side, there is a lot of interesting material, like including graphite or graphene or whatever the intermetal, lot of metal oxides. Also, you can use something like somewhere here, somewhere if you use your chalcogenide, somewhere molybdenum sulfide, somewhere you may get somewhere the slightly higher potential we can get. Anyway, there is a lot of, at least the academic research you can do. Still, you can do research in the area of especially metal sulfides or whatever chalcogenide, etc. for the especially for the anode material development. So just till I'm telling that in terms of industry, they take existing material, something, then try to understand the surface coating, what are the maximum capacity they can recover, and they can concentrate on the technology. So these are the important materials. For example, NCM is nickel, cobalt, manganese, something like nickel-rich sample, slight air capacity, and other type of compositions. And iron phosphate is 3.5, etc. So what I'm doing, they each have advantage. Is still now major challenge is that anybody is having a breakthrough ideas, or either chalcogen and any whatever the way you want to try to prepare. If you may get something like 400 or 500 automatically, we can improve the, for example, energy density, as well as we can reduce further cost of the batteries. So these are the one example how we can get some bulk metal oxides, or you want to use carbon composites and nitrides, or nitrides we can prepare by using this type of the tube furnace. Either suppose, for example, you want to reduce this molybdenum 6 plus to 4 plus, we can use the carbon and we can get something like MOO2. So for example, the same thing is like MOS3 means sulfur, or MOS2 means there, because sulfur, so a little bit evaporating. The usual way is that either you can do in a seal tube reaction. Also, people can use this type of seal tube. They put some molybdenum source and sulfur source and heat high temperature. They may get some. There is a practical way of the sulfide, because of the that is the way we can do now. Nowadays, like hydrothermal approaches, for example, any molybdenum source and then sulfide source, then put together, and they can prepare the material. So it comes to this, anyway, this technique we can, for example, carbothermal reduction, we can use it, prepare a lot of the something like iron phosphate, etc. Here the iron 2 plus to iron 3 plus to 2 plus. That's why we have to reduce the, for example, if it is Fe2O3 source, then we have to mix with some carbon, make sure that iron has to reduce to 2 plus 2, sorry, 3 plus to 2 plus. So for example, here vanadium similarly like that way. That's why we can use, we try to prepare some of these are some metal cluster compound for the first time. Some nitrates look into very carefully this for the energy storage. applications. So this one example is lithium vanadium fluorophosphate, and nothing but the capacity like that way, 3 plus to 4 plus, and I think we need something good thermal stability. So it is very important. So always something like XRD you have to check, make sure that you get a desired phases or not, or once your material is ready, we can try to make something like electrode fabrication. You mix conducting carbon binder, all put together. Finally, coat it in the either alumina or copper current collector when this is ready. So later roll it, and suppose for example in lab scale you can do a small type of kinds button cell you can do, and finally dry the things and put in the glove box. Make sure that this cell is ready. You can fabricate in the glove box. Okay. So usually, suppose you want to be for example, in mobile phones, you try to cut in the pouch type of cell. Again, the fabrication is slightly different when compared to the, for example, kind cell fabrication. So usually for the industry, everything is automated, mixing, drying, and coating, calendaring, everything. They can put it now. Nowadays, a lot of different companies they're able to sell this type of the equipment. So anyway, this is academics. Always you try to prepare some kind cell, or including that R&D of the industry. They go for this one, make sure that they're able to get a desired phases or desired properties. So for example, this is cathode or not, or any chalcogenate, any material just coated on this particular thing, put separator, or sometimes lithium metal or graphite. Usually they use a lithium metal. Just make sure that we have to understand the potential, etc. Once you are very happy, either sometimes lithium containing compounds in combination with graphite, etc. we can use. So you try to make a button. The cell is ready. So the either you can do, for example, charge discharge means like charge and discharge potential of this particular material, and we can calculate the capacity cycle number, how long your battery is going to do. And as a good important point is that whenever you make a battery, so at least you have to see the voltage, for example 3.5, 3.9 or 4 or 4.2. Among all three type of non oxides, among them the top one is slightly higher energy density we can expect, because higher voltage. And as I told that energy density is nothing but voltage is cell into capacity. Anyway, we can do something similarly. We can do some XC2 or in situ XRD, and then something like impedance spectroscopy. So that will be useful to understand the mechanism. So in summary, so among them three cathodes, vanadium fluorophosphate seems to be slightly higher energy density compared to your other type of the cathodes. So now comes to some new vanadium based cathodes. Among them, these are the few compounds for the first time been reported, almost like compared to your iron phosphate. So nearly 4.1 Wi-Fi volt, we can see there's advantage. So again, we try to prepare samples either with simple stirring, and again, these are the, so remember any batteries, make sure that water has to remove. That's why we need to go to slightly around 150-degree temperature. Make sure that water is to remove, and we can, and then these are characterization techniques we've been used. And then these are the typically 4 volts cathode materials, real cathode, and then so capacity versus cycle number clearly shows that so reasonably good. Only is not very high. Still, there is a scope for this material either by appropriate. I think we can reduce the nanotech means particle size, or sync to appropriate electrolyte, etc. So again, I think we in terms of potassium batteries, again we look into, because we know that mobility of potassium is not compared to sodium. So potassium, we can get lower capacity. Anyway, after a few reports, I think recently some of recent our colleagues from Komaba have been already improved further using the appropriate potassium-based electrolyte. So another example, new materials is the Livpo4 cathodes. Again, these materials have been reported 2012 later. We something like we, including Professor John Goodenough and the Whittingham Novel, they've been extended this particular compounds, and they've been further improved in terms of especially by appropriate synthesis methods, and they use further improvement in the rate capabilities of this particular material. Anyway, we try to, early example is an hydrothermal approach, simple oxidate and LiPo3 with vanadium things, and then finally we heat the sample with appropriate, not to get a desired crystal structure. So these are again the 4-volt materials and 4.17 with the CV, and this one we can closely we're able to match and reasonably good rate capabilities. I mentioned that previously it's possible to HPO4 replaced by HPO4 replace HPO3 means oxalato phosphate. Again, this early example followed by something few other example also being worked. And then, so these are the few example on the low cost and high power grid applications. Again, for that cost is a very important point. Example is the sodium based materials are, so main reason is that ionic radius is slightly higher. There is a mobility issues. So quickly I'll mention that importance of the, for example, sometimes not only mobility issues, sometimes these sodium compounds, especially if you see, if you go for lithium to sodium by potassium, again sometimes is moisture sensitive, or sometimes you may keep keep in contact with water, it will get more reactive when compared to the lithium. So again, these are you see that nearly 4.2 volts we can get by using lithium based system, whereas the sodium based contained compounds we can get something like, so although we get some slight lower energy, irrespective compromising with respect to energy density, but the stationary application cost is also important. That's why sodium seems to be little bit, and also we can be more abundantly available. Again, still the technology has been a lot of challenge still have to solve. So nowadays, I think EV market, everybody is concentrating on lithium. Once maybe this technology is matured for another 5 to 10, maybe 10 to 15 years, then they may look for the alternative technologies. So I'm going to quickly the importance of some carbon coating in it, appropriate reasonably good rate capability. That's why the use of impedance spectroscopy, it will tell the importance of the good carbon coating. We get slightly lower resistance, etc. In summary, I think some people may ask you then in terms of cost not only lithium or sodium, like if you have other raw materials, for example, graphite, steel, and neodymium. These are all things whichever the country they have, they're able to produce. I think they can monopolize, or they can make a good thing marketing or whatever it may be. I think they will be, they don't need to depend on any other countries to get raw materials. So now quickly I'll go through some of the anode materials, because already I finished almost like 110 minutes. So I have another 20 minutes I have. So what I'm mentioning that this second part, I'll tell that what are the some few examples on the something like novel materials. Again, from there, so maybe some particular portion. So you may cover some chalcogenides, especially in this category, especially conversion based oxide materials. So already again I'm repeating the graphite fuel air graphene. So usually carbon-based graphite is more popular because of the lower discharge potentials. If you talk about your graphene fuel air graphene and graphene type of materials also, you may get something high capacity. Practically, this type of things may not be really useful for the practical system, because the reason is that voltage is not matching. And then sometimes, again, these are the few example with some of the example with the CVD means chemical vapor deposit grown graphene. So again, also we see something like based on our experience. So something like graphitic is really good in terms of the voltage. Again, I think sometimes this type graphene and graphene maybe use it for different type of applications, depending on the energy storage sensors, etc., and fuel cells, etc. So regarding anodes, I think different strategy. People use something like a nano-sized to nanotechnology, also an approach. Another is various of matrix element. So it's very important sometimes alloy forming elements, so that as a consequence you may get something like high capacity. And also we need something like matrix elements, like for example cobalt, vanadium, ruthenium, etc. We need to, or something like graphene or carbon coating is needed to improve the electronic conductivity. So anyway, in summary, with the help of various physical technique, XRD, TM, various different mechanodes have been proposed. So now I'm going to explain among all the 4 type of category, what are the bunch of materials are there. So I'll tell you the later. I think these are the most of the materials updated reference we have. So usually alloy-based materials. For example, the silicon and tin, it forming alloy forming element. If you silicon alone, you can use almost like 4,200 units. Okay. So again, tin we get 980. So that's why the slightly higher voltage. That's why more popular is that is graphite in combination with silicon. That's why sometimes they may use some small amount of silicon to the graphite matrix. That's why you may get, since the voltage is closely matching, so this combination people are using for the improvement in the energy density, capacity, etc. So anyway, other elements also there. Again, the voltage is slightly going to be up. So now, so these are the tin-based systems. I think I told you that this early report we've been working in from Japan, tin oxide. Later, from our group, in US, Singapore, we've been contributed to a lot of the interesting new materials we've been reported for the first time, starting from the uh, uh, well, for example, these are cubic type structures. Uh, I think it's ferroscite and pyrochlore and hollandite, etc. So again, the idea here is that tin matrix element, for example, these are tetragonal type structures. So again, the discharge voltage is 0.25 and charge voltage is 0.5 voltage, etc. So this one example is the new materials. Again, the vanadium-based system. So you see that either submicron size and nano size, we can, if it is nanomaterials, almost we can get something like reasonably good stability and then almost like good current rate capability, etc. So if it is submicron slightly, we can get something like slow capacity fading after 50 cycles. So we checked what are the possible reasons again with impedance, and we'll see that the minimal variation with respect, especially vanadium. If you go for other matrix element, iron and indium, somehow slightly lower capacity. So these are the few. Another example is the nanophase tin hollandites. So again, you try to prepare sample by using the solid state method. Again, nanophase we can reducing the ball milling approach. So again, as prepared and ball milling, you can see the difference in the particle size reduction, and these are the capacity cycle number. It clearly shows that. So this cobalt seems to be good matrix element for the lithium cycling. So especially this type of anode oxides, again, you see that binary oxides. I think there are a lot of, for example, spinols, etc. With some materials, especially are familiar. A lot of physicists, some materials also we can use it for not only batteries, we can use it for the magnetic properties, etc. For example, complex oxides somewhere here, molybdenum with a sheet-like structure means tungstates, or your molybdenum sulfide or oxide, all comes into this category. So that's why here chalcogenides, everything. The main issue is that irrespective of whatever it may be, the challenge is that especially discharge and charge potentials are slightly higher. So our job is that if you have any good tricks to reduce this discharge potential to further lower, that will be good for the practical application. Still, as academic researcher, still you can do. I'm not telling that you can stop. So, for example, you can prepare molybdenum sulfide, or combination of the dopants, or sometimes you can study the defect or interesting electrochemistry. If it is nano size, then we have to make sure that how the discharge and charge potential, especially first cycle and second cycle, you can compare. That will be interesting. What the electrochemical future of the, especially if you want to see the chalcogenides, any 2D material, just you want to see how much layer, etc. I think with the electrochemistry, it's very useful to how the lithium is going to intercalate. And depending on crystallinity or depending on the layer, your structures, your profile is going to vary. So that is my personal advice. So anyway, you can try to use a lot of the synthetic thing, compounds. So these are the few examples. If you're talking about another new materials and metal cluster compounds, also we can try to prepare either by simple carbothermal reduction method approach, or if you want to use something like graphene oxide, then it's called as exfoliated graphene. So advantage is that you can do something like some carbon coating we can get. So usual way is that you can mix something metal or aluminum-based oxide mix with carbon, and we can heat the sample near around 750 degree. So in argon atmosphere, we can get a respective something like complex lithium holmium oxides, etc. So these are the XRD patterns. So you can see clearly. So these are the different lattice parameters we are getting obtained by using the almost like different type of compounds. You can see, for example, LIY, MO3Y8. So whereas lithium holmium, MO3Y8, or sometimes manganese molybdate, so their C value is expanded. That's why you can see that expansion with higher C value as a consequence, uh, difference in the crystallographic representation. So again, I think we can do TM. These are crystalline materials. We can get some information about the interplanar spacing or something like shade pattern, etc. Also, some materials, for example, Mn2MO3, also we been studying Raman, just to make sure that how these are the new compounds. An early example, first time we will report with respect to temperature. We see the how the bonds and also IR studies, etc. So these are the another one, and also remember this some of the this studies, especially Mn2MO3, also magnetic properties also been studied. So I don't have time to discuss on this particular system. For example, sulfide sp2s3, either you can do something like lithium studies or potassium sodium studies. Again, somehow sodium seems to be good because of the especially anode side is that we can get a lower discharge.
Professor,
Yeah.
you have 5 minutes
Yes,
left.
yes, 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 sir. I'm going to finish. Okay. So
Okay,
already,
thank you.
yeah, 5 minutes. Okay. So and finally, so these are the sulfides. We can get something like, for example, this type of. Again, remember we have to get a voltage should be lower is better for the practical applications. I think I cover sometimes people are shown to be nitrites. Again, only 3 lithium can be reacted by using this a nitrogen containing sample, whereas the oxides 2 lithium as a consequence we can get an. So this is a way sometimes some if you want to design new materials or anything, so try to focus on whatever. For example, here again challenge is that how to reduce the voltage to this is a little bit good issue in this one. So again, something like a layer type, for example, similar titanium dioxide, titanium spinels among them, Elite 40A5 spinel is really good for the practical applications. So since the 5 minutes are there, I'll go through what are the another important, for example, TiO2, all people are familiar. So what I'm mentioning that with the molten salt approach, you can try to prepare sample with almost like high surface area materials. So, as you can see, 200 meters square with low temperature. Again, we can see the difference in the energy storage performance. So again, we can see the variation of the crystallite size, etc. So some reports, I think already we compared to our commercial sample, slight improvement in efficiency, and also recently, I think some other demonstration with the photo batteries in combination with the solar cells. I think again, see that some limitations are not like really 100% correct, especially in terms of the voltage. So I'm going to skip these details and the, for example, you can either some materials you can do something like sensors applications, or some of the, for example, if you don't have facilities, you can do something like with the liquid electrolyte with the supercapacitor application, etc. So again, I'm going to so again some if you are chemistry background, try to focus some organic based electrode. Again, the problem is that we can get something like lower energy density. That's why a little bit drawback for the applications. So I'm going to skip the details and the co-precipitates online. These are the different, for example, high rate capability. The iron phosphate seems to be good. So some of the other techniques I'm going to, since I have another almost another 1 minute. Again, so these are the different like material processing techniques you can do, or what are the material nanocomposite, etc. I can do. So what I'm telling that one quick slide, suppose some engineers are there, just make sure that there is a safety limit. How with the use of the in situ XRD, we can tell that okay. So for example, this particular batteries, you stop somewhere here, make sure that it stops. Otherwise, if you go to the higher voltage, sometimes you can remove the lithium. There is huge volume variation. Sometimes this cobalt oxide will react with electrolyte. Sometimes there is a safety issue. Sometimes it may catch fire. That's why. So suppose in case the supplier, they mention that we can stop somewhere 4.2 or 4.5. So accordingly, you have to fix the voltage. For example, if you're buying the cells from the commercial cells, etc. So I'm going to skip, you can do some fancy technique like a lot of other to understand the mechanisms, the X-ray absorption, etc. Again, this importance of the physical techniques are a lot of physicists we can contribute for example, X-ray absorption, etc. All the techniques will be very useful. I think one last slide is sustainability is very important. The research you do, make sure that almost like too many cells are disposing, and so we have to recycle in a proper way, and ecotoxicity, everything you have to avoid. And so among them, hydro and pyrometallurgy approach seems to be promising. So usual way the dismantling and discharging and treatment again. I think these are the way. There is a lot of other people like especially metallurgists or chemical engineers have to concentrate on the how to recycle the material, etc. So I think these are small conclusions instead of reading conclusions. I think I already am exceeded my time. So almost 6:30. So that so just I'm telling that again as a since this topic is and the workshop is on the 2D materials again the novel material again still I stress that especially this area also still we need something like long novel materials also needed for the especially to reduce the cost or we need something to improve the high energy density we need this type of thing. Again, I think important, although I discussed so many materials, among them few materials are promising. At the end, I think we need the cooperation with scientists and engineers for the large scale applications. And thank you very much. Maybe I'm happy to take a questions and answer. Okay. Thank you very much.
Thank you, Professor Reddy, for sharing a lot of works done by you, your group across the world. So it's nice. So already time is over. So maybe there are one or two quick questions. If participants wants, you can put on the chat box.
Or if it's later, if people are interested, maybe you can send me email also. There is no problem. So at
Yeah,
least, especially for the students are interested, I think that is very important. I think okay, if it's something useful. Some people are Dharma Dharai, some they raise the thing. Yeah, please, Dharma Dharai, please. Okay, yeah. I think some people have raised some questions. Yeah. So there is a problem with the internet. I think I don't know. So open a queue. How to press open a queue or what are the things I have to do? Some people have called Dharmadharai P. They have raised some hand. Maybe they're looking for the.
So Dharmadharai, you want to ask something? You can. I see you raised hand.
Or it is okay. I don't know.
So professor has shared his email ID there. So you can directly communicate with him
Yeah,
if you
yeah.
have
So
any
that.
query or guidance, maybe. So since we are already, lagging behind the time and we need to take a small exam, so let us go towards the conclusion of this session. So thank you very much, Professor Reddy.
Okay, sir.
It
Thank you,
was nice.
sir. And good luck. And again, thanks for the organizer, especially for your effort and making the very excellent program and excellent speaker, sir. Thank you very much. Thank you.
So thank you, sir, and hopefully we'll be in touch in near future and somewhere we'll meet. So thank you very much once again.
Okay. Okay, sir. Thank you very much, sir.
Okay.
Thank you, sir.
Okay.
Thank you.
So participants, now there will be a small MCQ based exam. So Ritanaba will share you the link. There will be 20 MCQ exams, 20 minutes, and time will count starts from the sharing of the link. Okay, so you please respond because this is mandatory as far AICTE ATAL Academy. We need to send the response to them. Then only they will issue the certificates. Okay, so Ritanaba,
Yes, sir.
you can proceed for
Yeah,
the.
thank you. Thank you. Thank you. So since I have shared the assessment form at 4:04 p.m., so it will be ended at 4:24 p.m. So there will be 20 minutes for 20 MCQ questions. Thank you.
So you can share the link in WhatsApp also.
Yes, sir. ये तो bro इसी से मॉल है पूरा वही कुछ नहीं oh sorry